After studying this module, you shall be able to learn the application of non-parametric tests to ordinal data with one independent variable and with two levels. Learn the concept and application of non-parametric test, Mann Whitney for between subject design, and learn the concept and application of Wilcoxon signed rank test for matched pairs, and understand the use of IBM SPSS 20 for these two tests. Applying non-parametric test to ordinal data with one independent variable with two levels. In the previous modules, we have understood the concepts pertaining to the application of parametric tests to the data with one independent variable. The research, however, is not that simple. The independent variables may be more than one, with each having multiple levels. The aim of the researcher may be to evaluate the differences between the two levels of an independent variable. The data may be in at least ordinal scale of measurement. Like, an investigator wishes to study if eating chocolates helps in recovering from depressive thoughts among students of psychology and sociology in the college. The response may be taken on the basis of rating on 5-point scale, strongly agree to strongly disagree to statement eating chocolates makes one happy. The design of such a research can be shown using the simple diagram where the group within subject or between subject design is taken and the independent level can be of two levels, level 1 and level 2, and the observations are taken. When the data is in the interval scale of measurement, the application of parametric statistical tests like Z and T is recommended. The reader may refer to the related modules for the understanding of these two statistical tests of parametric. The non-parametric inferential statistical techniques can also be applied to the data that does not conform to the assumptions of parametric tests. The current module focuses on two such methods that deal with data in at least ordinal level of measurement with two kinds of design: between subject design that uses the Mann Whitney test and within subject design that uses the Wilcoxon signed rank test for matched pairs. The ordinal data may be collected using the between subjects design or matched group within subject design. We shall study both these non-parametric methods in the coming parts of the module. The Mann Whitney test for between subjects design. The concept of Mann Whitney test. When the data is in at least ordinal scale of measurement, the Mann Whitney test may be employed to study the differences between the two independent groups on the selected variable. The Mann Whitney test, also sometimes referred to as Mann Whitney and Wilcoxon test, is one of the most powerful non-parametric tests and is comparable to the parametric counterpart, the student's Ttest. Whenever a researcher is unable to comply to the parametric test assumptions and the data is at least in ordinal scale, the Mann Whitney test is a very useful and dependent alternative. The assumptions of Mann Whitney test. The distributions in the population of the two groups to be compared are the same. So, the test can be used when the distributions are not normal. The scores are independent of each other. The test is not as restrictive as the t-test and can be used when distributions are not normal. Applications of Mann WhitneyU-test. The Mann WhitneyU-test is a robust non-parametric test that can be applied to the research data and it produces reliable results. But the following points need to be kept in mind by the researcher for a judicious application of the test. The data gathered does not comply to the assumptions of the parametric statistical test. When the data is in at least ordinal scale of measurement. When the researcher employs two independent samples and aims to study the difference among the two on the selected variable. Effect size. There is no straightforward way to present effect sizes for non-parametric tests, which involve small sample size. However, for many non-parametric tests, 20 to 25 participants is considered sufficiently large and an effect size can be calculated for them. The power of the test. The power of non-parametric test tends to be reported in terms of their comparison with their parametric equivalents when their assumptions are fulfilled. When the assumptions of the parametric tests are not fully met, non-parametric tests are more powerful than their parametric counterparts. So, in the research situations where the design is between subjects, it has one independent variable with two levels and the requirements of the parametric t-test are not fulfilled, but the measurement is at least ordinal, then the Mann WhitneyU-test can be used with more dependability. The numerical application for Mann WhitneyU-test. Let us explain the concept of Mann WhitneyU-test by taking up a numerical example. The problem is, a researcher wishes to study the effect of mild electric stimulation on the lower back pain among multiple sclerosis patients. 40 persons who have multiple sclerosis comprise the sample. The average age of the participants is 42 years and there are 28 females and 12 males comprising the sample. The 40 subjects are randomly assigned to the two conditions group. The group A received mild electric stimulation while the second group, group B, received the placebo. That is, there was no intervention shown, but the group felt as if they are receiving the intervention. The outcome variable is the pain improvement measured by McGill Pain Questionnaire, and the table below presents the data. The table A given here gives the data received on mild electric stimulation condition compared to the placebo in MPQ. We can see the columns that give the mild stimulation and placebo groups and the scores obtained by the two groups on the MPQ. The next column, that is given by rank, we will explain as we proceed with the numerical application of the test. Let us decipher the steps to be used for calculating the Mann WhitneyU-test. The value of N1 and N2 are determined by assigning N1 the value of number of cases in the smaller group. The number of cases in the larger group is denoted by N2. The scores obtained are ranked, that is, put in order of magnitude on a single scale by combining the groups. So, observations are combined from both the groups and ranked in order of increasing size. the lowest ranks are assigned to the smallest algebraic value, as we can see in the table. The ranks assigned vary from 1 to n, where n of course is the sum of small n1 plus small n2, that is the sum of the two groups n1 and n2. One must take care that tide observations are given the average of the tide ranks, and one must be careful while ranking the scores that each score's affiliation to its group is not lost. Once the ranks have been assigned, the value of u is calculated. To calculate the value, the size of n1 and n2 is considered to be important. There are two possible situations. Case 1, when n1 and n2 are less than or equal to 10, the exact probability associated are given in the table of Mann-Whitney directly in the statistical books. The table gives the lower and upper tail probabilities for the statistic u. The case 2 is when n1 and n2 both are greater than 10. The sampling distribution of u approaches normality in such circumstances. U may be converted to z, and the table relevant to the area of z scores may be used. Once the observed value of u has an associated probability equal to or less than alpha, then we reject the null hypothesis in favor of the alternative hypothesis. The u statistic is calculated as shown in the formula. U is equal to n1 n2 plus n2 into n2 plus 1 divided by 2 minus R2. By substituting the values from the table, we arrive at the u value of 280. As n is greater than 10, this u needs to be converted to z by following the equation given below. To convert the u value into z, we need to apply the formula zu is equal to n1 n2 divided by 2 minus u, and this is divided by the square root of n1 n2 into n1 n2 plus 1, and it is divided by 12. By the application of the numerical quantities and substituting them in the formula, we arrive at the u value of 280 as converted to z as minus 2.2. As one compares from the z table, z n equal to 40 equal to minus 2.195, where the probability is greater than 0.005. The comparison between the mild electric stimulation conditions and the placebo did not generate a significant difference in pain improvement, and thus the null hypothesis may not be accepted. We can also use the IBM SPSS commands for Mann-Whitney Ttest. The steps used for the SPSS application for Mann-Whitney Ttest are: select Analyze, Non-Parametric Test, click on Legacy dialogs, 2 independent samples, click over your variables, which in this case pain improvement, an under test variable list, and grouping variable, which is mild electric stimulation in this case, and click on options. Check descriptive and click continue. Click on Mann WhitneyU under test type. Click on define groups and type A1 next to group 1 and A2 next to group 2. Then click continue and click OK. These steps would produce the output for the comparison of the two chosen groups and add them to the output. The Wilcoxon sign rank test for matched pairs. The concept. The Wilcoxon sign ranks test for matched pairs is the non-parametric alternative to the dependent samples Ttest of parametric statistics. When the data collected by the researcher is in at least ordinal scale of measurement but does not comply to the parametric assumptions, the Wilcoxon test proves to be a powerful application to the data to analyze the differences between the two groups with related scores. Assumptions for the test. The Wilcoxon test is a non-parametric statistical test and is considered distribution free. The test does not assume normality and homogeneity of variance to be necessary perquisites for the data. It is important to know that the observations are independent from each other and there is some degree of continuity of the variable used. The Wilcoxon sign ranks test assumes that the distribution of the difference scores between the two conditions forms a symmetrical distribution in the population. Thus, it is a less restrictive test as compared to its parametric equivalent, the Ttest. Applications of Wilcoxon sign rank test for matched pairs. The purpose of the Wilcoxon sign ranks test with matched pairs is to compare mean ranks differences between two groups with related scores. There is one independent variable with two levels. The test is used for discrete ordinal dependent variable. Although a continuous dependent variable can be used, but the observed continuous scores have to be converted to ranks in this test. The scores are related to each other, that is, they are dependent scores. The scores are obtained on the matched participants or the same participants twice. The following may be kept in mind by the researcher while applying the Wilcoxon sign ranks test for matched pairs to the data. The data is in discrete ordinal form. If the dependent variable is continuous but does not comply to the parametric assumptions, the test can still be used by converting the observed scores to the ranks. There is one independent variable with two levels. The statistical research design chosen is within group research design, that is, scores on the same or matched participants are obtained twice. The test is a non-parametric alternative to dependent samples Ttest. It does not necessarily comply to the assumptions of normality and homogeneity of variance. The Wilcoxon test has almost the same power efficiency as the Mann WhitneyU test. So, when the data does not comply to the parametric assumptions, the Wilcoxon sign rank test may prove to be a powerful alternative to the dependent samples Ttest. Numerical applications of the test. A researcher wishes to know if pain improvement changes if electrical stimulation is added and removed with the same participants over a period, let us say 2 months, and then restored again. The research design is repeated measure, as we are taking the same sample before the treatment and after the treatment. The independent variable is electric stimulation. The dependent variable is pain improvement measured by McGill Pain Questionnaire. As the data does not meet parametric assumptions, Wilcoxon sign rank test is used. The table B given below gives us the data and sign ranks for the first treatment and removed treatment scores. The table C gives the data and sign rank for the restored treatment compared to the removed treatment. So, we have two conditions or two sets of data. First is the first treatment and the removed treatment scores, and the other is the restored treatment compared to the removed treatment. The table B, which gives Wilcoxon sign rank test, first treatment scores compared to removed treatment scores, and of course we see the different columns, and at the same time we also see the first treatment score, removed treatment score, and the difference that the two scores have. Let us look at the first set of scores in the second row. The first treatment score, suppose, is 28 and the removed treatment score is 19. So, a difference of -9 is there, and similarly we do it for other scores, and then these differences are ranked and we have a sign rank for the scores with us. One can go through the table and understand how the ranking is done. Let us look at the other set of data in table C. For Wilcoxon sign rank test, when it compares restored treatment scores as to the removed treatment score, we find the column 1 giving us the scores of restored treatment, column 2 removed treatment scores, the third column gives us the difference in the treatment scores, that is removed minus the restored. The fourth column gives us the rank of differences, and the last column gives us the sign rank. We can go through the scores and see that the score of -21 has the first rank, and as it is a negative sign, 17 minus 20, 38 minus 17, minus 21 is the difference, we have a negative rank of 1. And one can proceed like that for the remaining scores also. The total is done and it is found that the rank differences are -210 and the total of the ranks is 210. The Z is calculated as T minus N into N plus 1 the whole divided by 4 upon the square root of N into N plus 1 into 2N plus 1 when it is divided by 24. On application of the quantities from the tables, we arrive at the value of Z as -3.92, and using similar steps one arrives at the following test statistic. Removed first treatment Z as -3.92 and the restored to first treatment Z to be 1.175. Using this numerical, we have understood how the rankings are done and differences are calculated and the Z value is found. Now we can use similar steps and arrive at the following test statistic. Removed to the first treatment Z as minus 3.92 as we have just demonstrated, and by following the similar steps, the remaining two combinations of the data, that is restored to first treatment, Z is found to be minus 1.175 and the restored to removed treatment Z to be minus 3.924. The Wilcoxon results show that two pairs of mean ranks of pain improvement are significant. The first treatment condition of electric stimulation produced significantly higher pain improvement when compared to the removed treatment condition. The Z, where n is equal to 20, was found to be minus 3.929 with the probability of less than 0.003. Additionally, the stored treatment conditions was significantly higher in pain and improvement compared to the removed treatment condition, where the Z with sample size of 20 is equal to minus 3.924. The probability of occurring of such a Z value at this sample size is less than 0.003. Hence, there was not a significant difference in the pain improvement between the first and restored treatment condition. The steps to be used for calculating Wilcoxon signed rank test. The following steps may be used to apply the Wilcoxon signed rank test to the data. For the matched pair of observations A and B, calculate the difference D between the two variables. Take care of the signs also. Once the differences are calculated, rank these differences without respect to the signs. If there are ties, then assign the average tied ranks to the tied differences. After ranking, prefix each rank with the positive or negative sign which the corresponding D has. Discard the D equal to 0 pairs and N is equal to number of non-zero D. Add all the positive ranks, T plus equal to sum of ranks with the positive signs, and similarly the significance of the calculated T can be checked depending upon the value of N. We can see all these steps in the preceding section of the numerical application that we have just discussed. The tables also demonstrate how ranking has been achieved and the signs have been prefixed. Now, the significance of the calculated T can be checked by depending upon the value of N. Case 1 is when N is less than or equal to 15. The probabilities associated with the T can be directly checked from the relevant statistical table for Wilcoxon signed rank test. If the probability of the observed T value is less than or equal to the chosen significance level, then reject the null hypothesis in favor of the alternative hypothesis. Case 2 is when our sample size N is greater than 15. In such case, the T is to be converted to Z using the relevant conversion equation that we just used in our example. Once the Z is calculated, the area under the Z table may be used. to determine the associated probability and arrive at a decision regarding the null hypothesis. Using IBM SPSS for the test. The following commands may be used for applying IBM SPSS 20 for the data. Select Analyze, Non-parametric tests, click on Legacy dialogs, 2 related samples. Click over pair 1 under variable 1, first treatment in given example, and click over pair 1 under variable 2, remove treatment in given example. Click over pair 2 under variable 1, first treatment in given example, and click over pair 2 under variable 2, restore treatment in the given example. Click over pair 3 under variable 1, remove treatment in the given example, and click over pair 3 under variable 2, restore treatment in the given example. Click on Options, check Descriptive and click Continue. Click on Wilcoxon under Test Type and click OK. Summary. The present module discusses the application of non-parametric tests, Mann Ttest, between group design and Wilcoxon sign ranks test within group design. The tests are non-parametric alternatives to Ttest, independent and dependent. When the data is in at least ordinal scale of measurement, the Mann-Whitney test may be employed to study the differences between the two independent groups on the selected variable. The Mann-Whitney test, also sometimes referred to as Mann-Whitney and Wilcoxon test, is one of the most powerful non-parametric tests and is comparable to the parametric counterpart, the student's Ttest. The text deals with the steps involved in the numerical calculation of the Mann-Whitney test. The Wilcoxon sign ranks test for matched pairs is the non-parametric alternative to the independent samples Ttest of parametric statistics. The test is useful for discrete ordinal dependent variable. Although a continuous dependent variable can be used, but the observed continuous scores have to be converted to ranks in the test. The scores are related to each other, that is, dependent scores. The scores are obtained on the matched participants or the same participants twice. The text discusses the numerical applications of the test and also gives the SPSS commands to apply to the data.